In this Math 30-3 transformations video, we will be focused on identifying translations, reflections, and rotations in all four quadrants of a Cartesian plane, as well as dilations. If you want a really simple description of the transformations of shapes, translations can be considered moves, reflections considered flips, rotations, turns, and dilations like changing the shape's size. First, a little background knowledge you'll appreciate. There are four quadrants on a Cartesian plane. Quadrant 1 is in the top right, Quadrant 2 on the top left, 3 in the bottom left, and Quadrant 4 in the bottom right. The quadrants are separated by the horizontal x-axis and the vertical y-axis. You can see the x and y coordinates are positive or negative depending on which quadrant they're in, which can be helpful when identifying transformations. Since we'll be transforming shapes in this unit, it helps to know that shapes are named by their capital letters, and that once we've translated, reflected, rotated, reduced, or enlarged them, that their new labeling includes those same letters with apostrophes next to them. Let's take a look at translations first. For example, firstly notice that the original triangle ABC is this one. We know this triangle is the image or new or translated triangle since it has the apostrophes. If we want to know how many units a shape has been translated, we should use corresponding points. So we can use A and A prime, or we can use B and B prime, or C and C prime. Prime is how we say the apostrophe. Point A has x coordinate 2 and y coordinate -2. A prime has x coordinate -4 and y coordinate 1. For translations, we'll simply count how far apart these points are. Remember, we started at A and ended up at A prime, so this triangle has been translated 6 units left and 3 units up. This is true of B and C as well, so it wouldn't have mattered which points we chose. Let's take a look at reflections next. Let's continue the triangle theme and discuss reflections using triangle DEF. There are 2 types of reflections we'll need to identify: reflections over the x-axis and reflections over the y-axis. The reflection over the x-axis looks like we folded the paper in half at the x-axis and traced our shape in the new location. A reflection of points in quadrant 3 over the x-axis results in all points now being in quadrant 2, and a reflection over the y-axis from quadrant 3 results in all the points ending up in quadrant 4. You'll notice the coordinates of the images, the transformed shapes, are directly related to the coordinates of the original. That will be helpful when you perform the reflections. For now, we are just identifying them.
Now, when it comes to identifying rotations, we will focus on clockwise rotations in this video. We will do 3 kinds of rotations: 90 degrees clockwise, 180 degrees clockwise, and 270 degrees clockwise. First and foremost, let's remember those quadrants. For this example, we'll be starting in quadrant 1. So we can see that 90 degrees, or a quarter turn clockwise, rotates this triangle into quadrant 4. Knowing which quadrant each point starts and ends in helps us predict what the rotation will look like. 180 degrees from quadrant 1, a half turn, would be quadrant 3. And 270 degrees, a 3/4 turn from quadrant 1, would end up in quadrant 2. This can be applied for any of the quadrants you start in. And in this case, we do want to pay attention to the coordinates of the rotation, as it may help us with what type of rotation has occurred. Let's use point H to demonstrate this. The coordinates on the original point H are +8 for x and +2 for y. When we rotate 90 degrees,
Point H primes.
coordinates are +2 for x and -8 for y. When we rotate 270 degrees,
Point H primes.
coordinates are -2 for x and +8 for y. This means that in general, when we rotate 90 degrees or 270 degrees clockwise, the coordinates values switch. When we rotate 180 degrees,
Point H primes.
coordinates are -8 for x and -2 for y, so the values stay the same. As for the positive and negatives, you'll notice that whatever quadrant we end up in decides which coordinates are positive or negative. This becomes more important when we perform the rotations. But remember, we're only identifying rotations in this video. Lastly, we have dilations. Triangles are some of the best shapes to demonstrate dilations, enlargements or reductions, since we're so familiar with their angles. We can see that these two triangles are similar to each other. Two figures are said to be similar when they have the same ratios of the lengths of their corresponding sides and their corresponding angles are equal. We know this is a reduction since we can see that this triangle has gotten smaller. In general, the original or old shape is on the left and the image or new shape is on the right. In order to calculate the scale factor of this reduction, we divide new by old, or the image's measurement by the original's measurement. So we see here that 8 divided by 40 equals 0.2, as does 11 divided by 55, as does 14 divided by 70. So we see the scale factor 0.2. What if the scale factor had been 1? Well, that would mean the shapes were identical and no change had occurred. An enlargement would have a scale factor bigger than 1. Here's an example of a scale factor larger than 1 for an enlargement. So when we identify dilations, we need to identify them as enlargements or reductions. We justify our reasoning mathematically by including our calculations of scale factor.